every type of space mission failure. Space is complicated. We make it simple. Space doesn't forgive mistakes. It doesn't forgive rounding errors. It doesn't forgive miscommunication between two engineering teams. And it definitely doesn't forgive a single wrong unit of measurement. Every category of spaceflight failure on this list ended a mission, and some of them ended lives, and almost none of them came down to one dramatic single cause. They came down to something small, survivable looking, that space simply doesn't allow room for. We're going in order of where in a mission things went wrong, from the launch pad to deep space, then we'll sort them a second way, by how preventable each one turned out to be in hindsight, because some of these were freak accidents, and some were warnings that got ignored. Launch failures. We begin at the most statistically dangerous few minutes of any space mission, the launch itself, where a rocket is structurally a controlled explosion pointed in one very specific direction. The most catastrophic example remains the Space Shuttle Challenger disaster in 9986, which broke apart 73 seconds after liftoff, killing all 7 crew members, traced to a rubber O-ring seal in one of the solid rocket boosters that failed to properly seal in unusually cold launch morning temperatures. Here's the fact that should genuinely bother you. Engineers at the booster manufacturer had specifically raised concerns about launching in cold weather the night before, and were overruled. The failure wasn't a mystery nobody saw coming. It was a known risk that got approved anyway, under schedule and public pressure. A single rubber ring, worth a tiny fraction of the mission's total cost, was the difference between a normal launch and a national tragedy. Here's the part that changes how you should think about every launch since. Launch failures remain one of the most statistically dangerous phases of any mission, specifically because so much energy is concentrated into such a short window. A rocket carries enough propellant to reach orbital velocity, meaning even a small malfunction in the first few minutes has almost no time to be corrected before catastrophic consequences. The Nun Moon rocket failures. Here's the fact that belongs earlier in this category, back at the launch pad, because it's arguably the single most dramatic example of launch failure in spaceflight history. The Soviet Union's Nun rocket, developed in secret as the USSR's answer to the American Saturn V in the race to the moon, failed catastrophically on all 4 of its test launches between 1969 and 1972, never once reaching orbit successfully. Its second test in July 1969 remains one of the largest non-nuclear explosions ever caused by human activity. The rocket lifted only a few meters off the pad before its engines shut down, and it fell back, fully fueled, destroying the launch complex in a blast that reportedly shattered windows in a nearby city. Here's the fact that should genuinely bother you. The Nun used 30 separate first-stage engines clustered together because Soviet engineers hadn't solved the problem of building a single engine large enough to do the job the way the Americans had, and coordinating 30 engines simultaneously without a sophisticated enough control system to manage vibration and failure cascades between them meant a single engine malfunction could trigger a chain reaction across dozens of others before ground control had any chance to intervene. The program was canceled after its 4th failure, its existence kept officially secret by the Soviet government for years afterward, and it remains the primary technical reason the Soviet Union never landed a crewed mission on the moon at all. Unit conversion and software failures. Here's the twist. Not every disaster requires an explosion. Some of the most expensive failures in spaceflight history came down to something you'd find in a middle school math class. In 1999, NASA's Mars Climate Orbiter, a probe that had traveled hundreds of millions of kilometers to reach Mars, burned up in the Martian atmosphere because one engineering team calculated thruster performance data in metric newton seconds, while another team's software expected the same data in imperial pound force seconds. A mismatch that caused the spacecraft's calculated trajectory to be off by just enough to bring it dangerously close to the planet instead of settling into the intended orbit. Here's the fact that should genuinely bother you. This wasn't a single person's mistake. The discrepancy passed through months of navigation checks without being caught because nobody at any review stage happened to compare the specific units both systems were quietly assuming. A $125 million spacecraft was lost after a 9.5-month journey because two teams working on the same mission never explicitly confirmed they were speaking the same units of measurement. It remains one of the most cited cautionary tales in engineering education anywhere in the world, specifically because the failure was so mundane and so completely preventable. Reentry and heat shield failures. Here's the reframe. Getting a spacecraft into orbit is only half the danger. Getting it back through the atmosphere at speeds around 28,000 kilometers per hour generates temperatures hot enough to vaporize most materials, and the entire survival of a returning crew or payload depends on a heat shield performing exactly as designed, with essentially zero margin for damage. The Space Shuttle Columbia disaster in 2003 traces directly to this category. A piece of insulating foam broke off the external fuel tank during launch and struck the leading edge of the shuttle's wing, creating a breach in its heat shield that went unnoticed or was assessed as non-critical throughout the 16-day mission. During reentry, superheated atmospheric gases penetrated the breach and destroyed the wing's internal structure from the inside, causing the orbiter to break apart, killing all 7 crew members. Here's the fact that should genuinely unsettle you. Foam strikes on launch had been observed on previous shuttle missions without catastrophic consequences and had gradually come to be treated as an accepted, non-critical risk rather than a warning sign, the same normalization of risk pattern that preceded the Challenger disaster 17 years earlier on the exact same overall spacecraft program. Communication and navigation loss. Here's the pivot. Sometimes a spacecraft doesn't explode or burn up at all. It simply goes silent, and nobody ever fully learns why. The Mars Polar Lander, launched by NASA in 999, the same year as the Climate Orbiter failure, lost contact with Earth during its final descent to the Martian surface and was never heard from again. The most widely accepted theory, based on ground testing conducted after the loss, suggests the lander's onboard software may have misinterpreted the mechanical vibration of its own landing legs, deploying as a signal that touchdown had already occurred, prematurely cutting its descent engines while still high above the surface. Here's the fact that should genuinely bother you. Because the spacecraft carried no telemetry system capable of transmitting data during the actual descent and landing sequence, a cost-cutting decision made earlier in the program. Investigators were left reconstructing the most likely cause from indirect evidence alone, never able to confirm with certainty exactly what happened in the final minutes before contact was lost. An entire spacecraft and the true story of its failure vanished into the Martian atmosphere together, leaving engineers with an educated guess instead of a definitive answer. Deep space and interplanetary failures. Here's the fact that changes everything about how you should think of failure on this list. Sometimes a mission's own success creates the danger that eventually kills it. The Soviet Union's Phobos 1 probe, launched in 1988 toward Mars's moon Phobos, was lost partway through its journey after ground controllers uploaded a routine software command containing a single character typo, accidentally disabling the probe's attitude control thrusters and causing it to lose its lock on the sun for solar power, permanently draining its batteries in the cold of deep space. Here's the part that lingers about this category specifically. Interplanetary missions operate on light delay communication, sometimes many minutes each way, meaning ground controllers can never react to a developing problem in real time. By the time a concerning signal reaches Earth, whatever caused it has often already run its course, for better or worse, millions of kilometers away, with no possibility of a timely human intervention. Every interplanetary mission is, in a very real sense, an argument that the engineering was good enough on the day it launched to survive months or years of complete isolation, because there is no version of "we'll fix it once we notice" available, once the spacecraft leaves Earth's immediate neighborhood. Human spaceflight emergency survived. Here's the fact that closes this list on a rare, genuinely hopeful note. Not every catastrophic failure in this category ended badly. Apollo 13, launched in 1970, suffered an oxygen tank explosion partway to the moon, crippling the spacecraft's primary power, water, and life support systems roughly 200,000 miles from Earth. A failure that, by every reasonable expectation, should have killed all three astronauts aboard. Here's the fact that should genuinely inspire you. The crew and mission control, working together under a strict, unforgiving deadline of the crew's dwindling oxygen and carbon dioxide filtration capacity, improvised a solution using the lunar module as an emergency lifeboat and built an improvised air filter adapter, quite literally out of plastic bags, cardboard, and duct tape, following instructions relayed from the ground under conditions where a single additional failure would have been fatal. All three astronauts returned safely to Earth. Here's the part that lingers. Apollo 13 is remembered today less as a failure and more as one of the greatest engineering rescues in human history, proof that this entire category of catastrophic space failure doesn't always end the way the previous 5 entries on this list did, but only because an enormous amount of expertise, improvisation, and functioning redundancy happened to be available at exactly the right moment. The Beagle 2 mystery. Here's the fact that closes out an entirely different flavor of loss on this list. The British-led Beagle 2 lander, which separated from its mothership and attempted to touch down on Mars on Christmas Day 2003, simply went silent, with absolutely no signal ever received after separation. For over a decade, its fate remained a genuine, unsolved mystery. No debris, no confirmed crash site, nothing, until high-resolution images captured by NASA's Mars Reconnaissance Orbiter in 2015 finally located it, sitting intact on the Martian surface, remarkably close to its intended landing site. Here's the fact that should genuinely bother you about how this one actually ended. Beagle 2 hadn't been destroyed at all. Its solar panels, arranged like petals designed to unfold in stages after landing, appeared to have only partially deployed, most likely blocking the lander's radio antenna and preventing it from ever transmitting a single signal back to Earth, despite the lander itself surviving its landing successfully. Here's the part that lingers. For 12 years, an entire mission was written off as a catastrophic, unexplained failure, when the true story was almost mundane by comparison. A probe that landed safely, functioned exactly as designed in every respect except one, and sat quietly on the Martian surface the entire time, unable to say so, over a mechanical snag no more dramatic than a folding chair that wouldn't quite finish opening. Sample return and robotic near misses. Here's the fact that closes out the robotic side of this list. Not every failure ends in total loss, and some of the strangest stories on this list are the ones where a mission almost failed, caught its own mistake, and kept going anyway. Japan's Hayabusa probe, sent to collect a sample from the asteroid Itokawa and return it to Earth, suffered a cascading series of failures during its mission. A fuel leak, the loss of 2 of its 3 reaction wheels used for orientation, and a period of total communication blackout lasting nearly 2 months after engineers lost contact entirely. Ground controllers, working with a spacecraft they couldn't reliably talk to, and that was tumbling in an unknown orientation, spent years improvising workarounds, including using the probe's ion engines in a configuration they were never originally designed for to compensate for the failed reaction wheels. Here's the fact that should genuinely impress you. Despite years of near total failure, Hayabusa limped back to Earth in 2010, 3 years later than planned, and successfully delivered tiny grains of asteroid material in a sealed reentry capsule, the first sample ever returned from an asteroid, retrieved by a spacecraft that, by any reasonable engineering standard, should have been declared a total loss years earlier. Let's sort these 8 again a different way, not by mission phase, but by how preventable each one turned out to be in hindsight. On the known risk ignored end, the Challenger and Columbia disasters, both preceded by specific warning signs that were assessed, documented, and ultimately accepted rather than acted on. On the purely mundane end, the Mars Climate Orbiter, lost to a unit's mismatch that any single cross-check at any point in months of review could have caught. On the genuinely uncertain end, the Mars Polar Lander and Phobos 1, both lost to failures that investigators could only partially reconstruct after the fact, without full certainty. And on the survived against the odds end, Apollo 13, a mechanical failure just as catastrophic as several others on this list, saved only by exceptional human performance under the most unforgiving deadline imaginable. Every category here shares one grim thread. The margin for error in spaceflight is thin enough that something as small as a rubber ring, a mismatched unit, or a single mistyped character has, at various points, been the entire difference between a successful mission and a national tragedy. It's worth acknowledging before we close that failure on this list wasn't distributed evenly across history. It was concentrated disproportionately in the earliest years of any given technology or mission type, then dropped sharply as institutional knowledge accumulated. Early rocketry in the 1950s and 1960s failed at a rate that would be considered completely unacceptable by any modern aerospace program, simply because nobody yet had the accumulated data to know what would go wrong. Every disaster on this list, in some sense, became part of the reason later missions succeeded. Challenger's O-ring failure fundamentally changed how NASA assessed engineering risk under schedule pressure, and Columbia's foam strike rewrote how in-flight damage gets assessed during every subsequent shuttle mission. Here's the part that lingers. The failures described here weren't random bad luck scattered across an otherwise smooth history. They were the tuition, paid in some cases with human lives, for essentially everything spaceflight now knows how to do safely. Here's the last thing worth sitting with. Every successful spacecraft launch, landing, and mission you've ever heard about shares the exact same fragile margins as every failure on this list. The same thin heat shields, the same unforgiving unit conversions, the same total dependence on nothing going wrong for months or years at a time, millions of kilometers from anyone who could help. Success in spaceflight isn't the absence of these risks. It's the same risks every single time, simply not going wrong that day. Not bad for stick figures on a rock.